In the next 15 minutes, I'm going to teach you binary reverse engineering. By the end of this video, you'll be ripping apart binaries in IDA. You don't need any programming experience or any cybersecurity experience whatsoever. Let's get into it. To discuss how to do reverse engineering, we first need to talk about what reverse engineering is. The art of reverse engineering is taking a binary and reversing it to figure out what it does. To talk about this, let's talk about what the classical example is of source code that goes from source code to a binary. When I write code, I have a bunch of different symbols in the binary that are human readable. I have the type of the variable, I have the name of the function, I have the name of the variable, etc. All of these symbols, these human readable strings, these labels, tell me what the code is going to do. I can infer a lot of information from the source code by reading the code. So for example, I have a buffer that gets passed to scanf, and then I call getPass on that buffer. Because I have the source code, I now know generally that I will read in data from the user and I will check that buffer against a known password. And if I get it right, I get to go to the that is correct block. The problem is that if I have just the binary, I don't have that source code. And instead what I have is this really horrific, just binary blob of data that looking at this, I can't infer any information about this. So reverse engineering is going from this without the source code and inferring the features from what the code does, right? Why do we do that in the first place? The number one thing I think is for cybersecurity professionals, the art of malware reverse engineering is extremely important for a few reasons. The big one being, if you're able to take the malware that you find in your system and triage it by hand, instead of depending on a sandbox analyzer, you can yourself figure out what the attacker was trying to do, and then from that infer how to defend against it. Number two, I think reverse engineering is just fun. I think the art of taking things that you don't know what they do, looking inside of them and figuring out what they're supposed to do is really fun. So there's a couple different techniques that we can do to reverse engineer this binary. The first one that everyone can do right now on your computer is we can do the operation strings on our binary. So we're going to do that. All the strings binutil does is it looks for a 5-character or greater string of ASCII characters and prints them to the screen if they're found in the binary. So these are all the strings in the binary, and you can see we have the name of the functions that we import, like scanf, puts, and printf. Those will always get preserved for the reasons of linking. And then we have the strings we actually wrote into our program. We have welcome to your first crack me problem. What is the password, the format string for the scanf, and then that is correct. The problem with this is that the password itself is not revealed in the binary. So we have to go through the art of getting a little deeper, reading the machine code and figuring out what the machine code does to get the password from the user. Going one level deeper, instead of strings, we can kind of put this into what is called a disassembler. The one disassembler everyone has access to right now is going to be object dump. So we're going to write object dump, disassemble the main sections, use Intel syntax on our program, and pipe that into less. Now what we have here is the disassembler is taking the ones and zeros, the literal hex data, and converting that into a human readable version of the assembly instruction. So if we navigate down to the text section, the text section contains the code for our binary, right? The executable bits that will get ran by the processor. And here we have the binary data and then the actual human readable assembly instruction. The problem with this now is this is not very human readable. We can probably kind of infer what's happening here, but there's not a good visualization of the control flow graph, meaning the if statements that will either execute or not execute as the binary runs. So we're going to go one level deeper and put the binary into a more complex disassembler. And my favorite disassembler, there are two primary ones. There's IDA and Ghidra. I would argue for the reasons of learning assembly and learning reverse engineering that we should use IDA. So we're going to go ahead and we're going to install that. I've already installed the downloader. I'll put the link for that in the description below. From my downloads, you can go ahead and run the IDA installer. And once you've ran the installer, you will get a folder in your home directory called IDA free, and we're going to run IDA 64. We're going to go to baby's first crack me, and we're going to import our binary file. It's going to make sure that we are okay with us treating this binary file as an ELF64, and we're going to go ahead and hit OK. What IDA will then do is IDA will go through and it will disassemble the entire binary and give us the ability to read the assembly here. I'm going to zoom in on this. And now we are looking at IDA's disassembly of the program from what it inferred as the start point. So the start point is what is the first instruction that is going to run when the program starts. There's a lot of stuff here that we can talk about, but this is more about the runtime of the libc library initializing. We're going to skip all of this. We're going to jump right into this label here. So before libc start main gets called, that's what the call instruction does, it loads the effective address of our main function into RDI. So one thing we have to kind of talk about here, very basic reverse engineering concept, is this concept called binary ABIs, or abstracted binary interfaces. What these are the agreement that the computer has made with the processor about the registers that will contain different values when a function is called. So for example, if I call function foo and numbers 1 and 2 are the arguments to foo, before we call foo, RDI will contain 1 and then RSI will contain 2. This is just the agreement that the compiler has made with the processor, right? This is the way that it expects the data to behave. So if we go back and we look at that, when we call libc start main, we have RDI goes main and then, oh, I'm sorry, I guess in this case it's RCX. Actually, no, it is RSI. RSI takes argv, that's the second argument, and then RCX gets the next argument, which is init. So we're gonna go ahead and we're gonna double click on main, and this is our function that we wrote. You know, before we were looking at the libc start, we didn't write any of that code. This is the code that we wrote, but the assembly for that code, right? And we can kind of see that. If we look at this, we see we have the puts function get called, and it gets called with this pointer to S in RDI, argument number 1, and that's where it says, welcome to your first crack me problem. We then have another one that says printf. Printf gets called on the what is the password. So these are the two prints that get called to prep us to check our password. And then we have a few things happen here. So remember how I said that the first argument is RDI and the next argument is RSI? Well, we can look at this move instruction and see that RSI comes from RAX. We're going to middle click on RAX. These all get highlighted. RAX becomes load the effective address of this location here. Interesting. What is that location? So because it loads the effective address, it actually puts a pointer to this location in RIX before it puts it into RSI. So that means that this variable here, variable 50, is the buffer that we created for our buffer. Remember, we can go back and look at our code here. We created a 64-byte buffer, so that is the location of where our password is going to go into. Okay, so let's go ahead and we're going to label this. We're going to right-click, hit name, we're going to type in buffer. By doing this, we are starting to infer more and more information about the symbols that we wrote as programmers, that the malware author wrote as a programmer, the malware reverse engineering or whatever, about what the program does, right? So we call the scanf function here, and then eventually we go down to this next function here, and then we have a conditional jump. We say jump Z or jump 0 to either this location that is correct or something else. We're going to talk about how that all works in a second here. So again, we talked about the binary ABI. The binary ABI tells us, what the processor agrees on in terms of what registers receive what data. In the case of return values, and again, this only applies to 64-bit Intel, return values come back through RAX. So we're going to keep that in mind. So arguments go into RDI and RSI, and then return values go into RAX. I just realized my fat head was blocking that. I apologize. All right, so if we go back into the VM, we see that we call this function. The processor then tests EAX, which is the lower half of RAX, so it tests the return value. And if the return value is 0, we jump, the green line is where we jump on a positive test. So jump 0, we jump around this. And if it is not 0, jump 0 red, right? The red means we go here. It says that is correct. What is that coming from? If we go back to our code, we're testing the return of the getPass function. The getPass function will return 1 if our password is correct, and if it's correct, we say that is correct. So that's how we got that out of the assembly. So now you're probably saying, okay, cool, let's get into that function. Let's go figure out that password. Okay, we'll get there. Step 1, we want to rename this the get password function, right? We can just kind of infer that, it says, what is your password? If you get it right, it says that is correct. We can just infer that that is the get password function. So we're going to double click on that. And here we have this giant chart. You may already see the password starting to appear here. But remember what I said before, the RDI variable is the first argument that gets passed into a function. In this function here, we passed our buffer as the first argument, so we're going to go into there. So if we look at this, it does a few things. It sets up our stack, and then we move RDI, the pointer that we gave it as an argument, to another variable on the stack. It's preserving the argument. So we're going to call this buffer as well. And this is a pointer to the buffer. So now what it's doing is it's going to take that same buffer, it's going to put it into RIX, and it's going to compare the first pointer or the first byte. So say treat RIX as a pointer, extract 1 byte, and put it into EAX. That is what this instruction turns into. And we're going to compare that. AL is the lower 8 bits of EAX and RIX. These are all the same registers, just different parts of it. And we're going to compare that to 63H. Well, as IDA is already showing you, IDA is showing you, hey, by the way, 63H is the letter C. If that is not 0, right? If they're not the same, a 0 comparison is also the same as the same comparison. So if they're not 0, meaning that they're not the same, jump away. And this is the return, right? We are returning 0. So if we go back, if it is not 0, or if it is 0, meaning that they're the same, go to the next, add 1 to our pointer, right? Extract the buffer, add 1 to it, which means increment to the next character, and compare that to the letter A. So we can actually just read the instructions here and figure out what our password is. So CAN, okay, that's a word, can underscore ya underscore Kanya underscore dig underscore it question mark. Okay, cool. So that seems easy enough. Let's try it out. Can ya dig it? That is correct. What did we just do? We took a binary that we didn't have the source code for, and again, we did, but we weren't referencing that too heavily, and we put that binary into first object dump to figure out what it did, but we saw this was kind of ugly and hard to read, so we put it into our favorite disassembler, IDA, and use that to extract the functionality and eventually the password. You may be asking, why did strings not reveal the password in that binary? The reason was, when you look at this, the actual hex code for the binary is the instructions at that location. The comparison to the letter G actually gets packed into the instructions. If you look at the instruction here, you don't get to see the letter G packed into the binary. Actually, you kind of do. You can see the letter G here gets packed into the instruction because we're comparing that byte to the letter G. But again, you wouldn't know that if you didn't know the functionality of the binary. So I highly suggest you go onto my GitHub, links down below, take the IDA link also below, and try this out for yourself. I'm a huge proponent of kinetic learning, using your hands, getting dirty, and feeling things out as you go. That is the same reason why I'm excited to talk about today's sponsor, Brilliant. Brilliant is an amazing learning platform that features over 70 courses and a variety of interesting topics like math and computer science. Brilliant's computer science course covers a series of bite-sized lessons on the fundamentals for professional programmers like logical decision-making, interfaces, and thinking with graphs. My favorite part about Brilliant is that their lessons are all hands-on. I'm someone who learns by doing. Every Brilliant lesson is filled with interactive examples that let you test your understanding as you go. You can go try Brilliant for free right now, and using my URL, www.brilliant.org/low-level-learning, the first 200 of you get 20% off an annual premium subscription, which gives you access to all of Brilliant's courses. Thanks again, Brilliant, for sponsoring this video.